So good morning. Actually, before I begin, I have actually bad news to report, but it's probably worth reporting, so let me do that. I got an email yesterday that Bert Richter had passed away. I don't know how many of you know who Bert Richter is, but don't bother to raise your hands. He was one of the great experimental particle physicists of the 20th century. He won the Nobel Prize for his share of the discovery of the J-psi. Actually, the J-psi was discovered by Sam Ting in proton-proton collisions, Drell-Yan production of a J-psi, which then decayed to mu plus mu minus, and more or less at the same time by a group at SLAC who used one of the first E plus E minus colliders to produce the J-psi as a resonance in E plus E minus. And Bert designed really both the machine and the detector. The machine was one called SPEAR, which ran between about 2.5 and 6 GeV in the center of mass. And it was just in the right region to make many of the great discoveries of particle physics. The J-psi, the tau, the jet, the fact that E plus E minus to quarks materializes as jets, the fact that the cross-section for that reaction, when you compute it in QCD perturbation theory, you get the right answer, which makes no sense because it's strong interactions. But nevertheless, all these things really were the foundation of the Standard Model. And so this is a picture of Bert contemporaneous with the SPEAR construction. And if you look at the blackboard, those are the equations for the accelerator physics of the SPEAR ring. I have one more picture to show, which is the leaders of the Mark I experiment at SPEAR. So this was actually the first ever 4-pi detector at a colliding beam machine. Bert had the vision that whereas particle physics up until then had been done with fixed target and then with detectors with very small acceptance, at a colliding beam machine you had to have a 4-pi detector with basically tracking, magnet, calorimetry, muon system outside. The Mark I was the first detector of that type. And basically everyone has copied the model because it's been extremely successful. So the people in this picture are, Bert is here, Martin Pearl, who, maybe I should say, this Mark I detector was deficient in many respects. And the tau could not have been discovered had not Martin Pearl been such a brilliant experimentalist. And then this is Gerson Goldhaber from Berkeley, who was the other senior member of the team. And he actually never did win the Nobel Prize, but he has a major accomplishment, which is the discovery of the charm mesons at SPEAR. All three of them are gone now, unfortunately, to that great symposium in the sky. But these guys were really giants, and somehow we have to live up to the standard that they set. What's on the screen here is actually quite interesting. It's the following picture. It's an event display for the reaction E plus E minus, going to psi prime, going to pi plus pi minus, psi going to mu plus mu minus. So as we would say at SLAC, it is the psi particle, not the J particle, because it tells us so. So, those of us in the SLAC community are remembering Bert, and I hope you will learn more about him. He's a truly amazing figure. Okay? Good. Let's get to business now. Oh. Somehow the black slide did not get put on there. I'm sorry. Actually, could we fix this, Felix? Do you have that memory stick? Somehow the wrong copy got put on. Just excuse me a minute. Yeah, I didn't click that. Okay. If you would replace that figure slide, I'd appreciate it. Okay. So today we are going to talk about, so yesterday we talked about the standard model predictions for the properties of the Higgs boson and their tests at the Large Hadron Collider. So today I'd like to talk about, as it were, the next step in that program. So it should be one, sorry, is there a black? Oh, did I screw this up?
There is no black.
Oh, then I screwed it up.
Okay.
Let's try it one more time. I really did screw this up.
Can someone see if there's a light on the projector?
Yes.
Okay, third time is a charm. After what I told you yesterday, the next logical question to ask is, if you saw a deviation in the Higgs properties from those predicted by the standard model, I emphasized to you that the standard model predictions are extremely precise. I think with some foreseeable improvements, they will be at the 0.1% level of accuracy. One can then ask, maybe we can do a sufficiently accurate experiment that we can see deviations from these predictions. And then if we succeed in that, we will want to interpret these deviations in terms of some underlying new physics. And so this brings up the question of how you parameterize deviations from the standard model in a systematic way, so you can then take those parameters and relate them to general kinds of beyond the standard model theories. And so that's going to be the subject of the lecture today. I guess I'd like to emphasize that where we are now in physics, the standard model is established. So the purpose of doing precision experiments on the standard model is not to decrease the size of the error bars. The purpose of precision experiments is to discover deviations from the standard model that give hints about physics beyond the standard model, which go into the territory that Nathaniel has been describing. And so, well, how can we do this? I think it's particularly important, as we think about the precision study of the weak interaction, to put some attention on the Higgs boson. First of all, as I emphasized yesterday, all but one or maybe three of the parameters of the standard model are explicitly couplings of the Higgs boson. So all the mysteries of the standard model are really associated with that particle. Why is electroweak symmetry broken? Why does the spectrum of quark and lepton masses have the form it has? Where does CP violation come from? These are all really questions about the Higgs boson. And so maybe we'll only get the answers if we study the Higgs boson in sufficient detail. At the same time, I think our experimental knowledge of the Higgs boson, even though it may have sounded very impressive in the previous lecture, is actually not so great. I will argue to you in a few slides that the expected size of deviations from the standard model Higgs boson property is probably less than 10% in branching ratios. And as you see, we're not there. And if you think that you need to see a 10% effect at 3 sigma, or maybe 5 sigma, you would really like to get down to errors of 1% on the Higgs boson couplings. And right now we're at 20 or 30%. I guess I feel very strongly that the LHC is never going to get there. And I think many LHC experimenters agree with that conclusion. So we need some kind of new facility to do this, and I'll talk a little about that in the course of this lecture. So, can we get there? Well, that's part of the issue, and so to begin to study this, what we want to do is to have some, again, intermediate step that relates beyond the standard model models to deviations from the standard model and gives us some insight into how that works. So now, we've already seen one example where you can parameterize a general class of models in terms of some numbers, which you can then extract from experiment and learn something. And that's the case of the S&T parameters that I discussed on Tuesday. So now the question is, can we extend that understanding to more or less any deviation that we might see from the standard model? And actually, there is a systematic approach to this that's been developed, which is called standard model effective field theory. Now, there are lots of different kinds of effective field theories. I guess next week Thomas Becker will give you lectures on effective field theory, and you'll learn about all kinds of effective field theories. But this is the one that's important to me for the task at hand, so I will give you a description of this insofar as I can. Okay, so we begin from the statement that the standard model is the most general renormalizable quantum field theory, with the fields being the known particles that we see in particle physics, and the gauge symmetry of the theory being SU3 cross SU2 cross U1. So any perturbation of that theory within the context of renormalizable theories, that is, operators up to dimension 4, is described just by changing the parameters of that model. In principle, there could be more general deviations, and so that's now what we'd like to talk about. Actually, the more general deviations have to be higher dimension operators, because all the dimension 4 operators have already been used up. And so we can write a general Lagrangian with the properties that I just listed, the known particle content and SU3 cross SU2 cross U1 invariance in the following form. The standard model Lagrangian, depending on the parameters of the standard model, plus some sum of Ci, OI, I'll put a tilde on that for the moment, OI6 plus DI, OI8 plus ... where these are operators of dimension 6, which are invariant under SU2 cross U1 and build up out of the known fields. These are operators of dimension 8, and then it goes higher. Now, a dimension 6 operator in a 4-dimensional Lagrangian has a 1 over m squared in front of it, where m is some mass scale. A dimension 8 operator has a 1 over m to the 4th, etc. So the way we should imagine that this effective field theory comes about is that there is some new physics at the scale m, which is much larger than, let's say, the weak interaction VeV scale of 250 GeV. Those particles cannot be produced because, at least at energies of a few hundred GeV, because all the particles in them are very heavy. So a way to understand what happens at our low energies, which are now, as I say, the Higgs mass or the W mass, is to integrate out those particles And then we get some generalization of the standard model Lagrangian, which is written in terms of only the known fields. And then we would expand that in powers of 1 over m squared. When we do that expansion, the various effects will take the form of local operators, as I've described. There will also be corrections of dimension 4 operators, and even dimension 2, like the Higgs mass. But whatever those are, we will shove them into here by changing the standard model parameters. Of course, we don't know what the standard model parameters are. We just get those from experiment anyway. So we don't know what the bare parameters of the standard model are. So when I integrate out this theory, most of the effects will actually go into a renormalization of the standard model parameters. But there'll be some residual effects left over, which are parametrized, as I say, by operators of higher dimension. Now, some of you might remember there are also a couple operators of dimension 5, some operators of dimension 7. Those all have to do with lepton or baryon number violation. The operators of dimension 5 are explicitly corrections to the neutrino masses. And so I'm going to omit those from this discussion, although, of course, if you're interested in neutrino masses, you may want to put them back in at the end. Okay. Now, this is actually already very important. On Tuesday, I told you that when you do perturbation theory, if you take the standard model and omit the top quark, you can find large effects which are of order the logarithm of, well, which are actually infinite. And when you put the top quark back in, you discover that it's the log of m top squared. If you have the top quark explicitly included, there are terms, so there, in standard model perturbation theory, there are terms enhanced like this, and terms enhanced like mt squared over mw squared. But as for new physics, it can't happen. The standard model is a complete theory. And so any effects that come from new physics, we can always shuffle into the standard model Lagrangian. And once we've done that, the corrections over here are always have an explicit 1 over m squared in front of it. So this is the reason for the statement that I just made. Corrections to the Higgs properties away from the prediction of the standard model are, by dimensional analysis, of relative order mh squared over m squared. And that estimate sets them at a few percent accuracy. So unless you're doing experiments of 1% accuracy or better, you're not in the game as far as understanding how the Higgs boson deviates from the standard model. Somehow we've got to get there, and so that's a very important challenge for the future of particle physics. Okay. Good. Now, there's obviously a problem if you want to do serious computation with this Lagrangian, which is that it is a non-renormalizable Lagrangian. And if you had a bad introduction to field theory, for example, the one in my book, chapter 10, you would say, well, we can't do anything with this theory because it has non-renormalizable operators. But that's not actually correct. What you have to do is approach the perturbation theory for this theory in a systematic way. And maybe I should say this is really essential when you do LHC physics with this Lagrangian, because at LHC you can't ignore NLO QCD corrections. And very often NLO electroweak corrections can come in as well when you look at very special processes like Higgs to 4 leptons or small regions of phase space that you would use to cut out the Higgs boson sample. So it's important to be able to do systematic perturbation theory with this Lagrangian. And I'm not going to do that in detail. I think probably Thomas Becker will give you some examples of how this is done, maybe not in this theory. But I'd just like to describe what happens when you compute one-loop diagrams in this theory. So let's imagine that we start with this theory and we compute a one-loop diagram. Now we will find various effects. Some of the effects that we'll find will be just the standard model effects. Those can include quadratic divergences in the mass term for the Higgs. There can also be quadratic divergences, which have the form lambda squared over m squared in one of these CIs, times, for example, a Higgs coupling. L dagger dot Higgs field tau right, for example. This coupling can get a quadratically divergent correction when you integrate out some dimension 6 operator. But that's fine, because this operator already exists in the standard model part of the Lagrangian. So we can just take this. It's really not correct to put lambda higher than m. So it's an order 1 correction. And we can shove that into the standard model part. So that basically takes care of all effects at the level of 1 over m squared to the 0. At the level of 1 over m squared to the 1, there are additional divergences. But when we look at this level, they're only logarithmic divergences. And what they basically are operator renormalizations of the operators OI6. So these can be effects of order alpha w times ci times log of lambda squared divided by m squared. And these are summarized in the operator rescaling of the OI6 operators in perturbation theory. So basically you have to compute the anomalous dimension matrix of the dimension 6 operators, and then this parametrizes the various divergences of this kind, which include operator mixing. You all know, I hope, raise your hands if you do know this, that the renormalization of operators typically involves operator mixing. For example, in the weak interactions. Okay, those of you who do not, leave your hands up. Those of you who do not have your hands up, ask for an explanation from someone who has his hand up or her hand up. Okay. Then there are also terms that you find in perturbation theory, which are 1 over m squared squared. And these terms can actually be quadratically divergent. So they can be of the form ci squared lambda squared over m to the 4th. And these terms basically, the quadratic divergences only appear in this way. And what these multiply is basically some operator of dimension 8. And so if the operator of dimension 8 was not in the theory originally, it can be induced by one-loop corrections. But properly, we don't know what the CIs or the DIs are. So you should be prepared to have arbitrary values for both the CIs and the DIs. And as you go further in perturbation theory, anything else you find. Okay, so this gets complicated. But indeed, one can control perturbation theory as long as you organize perturbation theory in a power series in lambda squared in a double power series in g squared and 1 over m squared. And so that's just what you have to do. And that theory organizes itself straightforwardly. And now we just have to consider all of the parameters of the standard model, plus all of the CIs, plus, as we increase the order in m squared, all of the other operators that appear as free parameters that we're going to determine by experiment one after the other. Hopefully, if m is large compared to the scale we're working with, it's a good first approximation to drop all terms beyond 1 over m squared. And in fact, for this lecture, I'm only going to work in the simplest circumstance, namely tree level in these parameters and ignoring all the other ones. But as I say, this is systematically improvable because that's a Lagrangian, and you just compute with it. Okay, now, in order to make this work, we need the complete list of the dimension 6 operators. And that's also got some subtlety to it. There's a theorem in quantum field theory that if you have some combination of operators which is 0 by the equations of motion, then the that combination of operators combined with other operators gives 0 in S-matrix elements. And so you're allowed to eliminate operators from this sum, which vanish by the equations of motion. So for example, if I take d squared on the Higgs field, that's equal to the Higgs potential, which, let me multiply by phi dagger over here. So this will give us, please excuse me, mu squared phi squared plus 2 lambda phi to the 4th, plus, if we include the dimension 6 operator, C6 is what it's called, lambda over v squared, phi to the 6th. But we can eliminate this operator from that sum in terms of the operators that appear in this series. And so there is some ability to systematically reduce the number of operators, but eventually there's a limit. And as we'll discuss, eventually you still get left with a lot of operators that you have to deal with, even in the first term of this sum. Maybe I should also say that there is a recent heroic work by Anish Manohar, Liz Jenkins, and Michael Trott that computes this entire matrix. And so basically they give you all of the logarithmic divergences that can appear in a standard model effective field theory calculation at one loop. It's a large matrix, as we will discuss. Okay. So now I guess what I'd like to do is to just change the notation very slightly in 2 ways. First of all, I remind you that, again, for the purpose of this lecture, I'm only going to work this far, and I'm only going to consider these operators at tree level. But if you want to go beyond that, I guess I've told you in words what to do. To do it in math, it's a little harder. The second thing is I'd like to exchange the things I called C tilde for some other choices. So in that expression, I wrote C tilde over m squared. But we don't know what m is, and it's nice to work with something that's definite. So in general, I'll work with something like C over v squared, where v is the Higgs vacuum expectation value. Sometimes I'll write mw here instead. It's a matter of convention how you define these coefficients. But I'm going to put a definite scale here. Then C is of order v squared over m squared. So as I say, it's expected to be small at the 5% or maybe few percent level if the new physics is well above the scale of the Higgs vacuum expectation value. And so basically the smallness of the CIs that we find can be traded for the scale of new physics, and in some sense encodes the scale of new physics. Okay? So now I'm going to write some explicit expressions which involve these parameters, and I'm going to explain how those expressions can encode various kinds of new physics effects, deviations from the standard model that hopefully soon we will observe in nature. Okay. Well, actually, it turns out that a lot of my personal history in particle physics is connected with this. And actually, one of the interesting experiences that I had early in my career was going to the Snowmass 1982 workshop. So this was the workshop that proposed the thing called the superconducting supercollider, which was the first big proposal for a large hadron-hadron collider actually, that thing had a 50-kilometer circumference. 2 years later, the Europeans said, oh, we can do this much more cheaply by reusing the LEP tunnel, and that's how the LHC was born. But this was the first time that a lot of theorists and experimenters got together and really started thinking seriously about how we would do experiments at the TeV scale. And one of the questions that they asked was, well, maybe quarks and leptons are composite, So how could we find out? So the thinking at that time was that if a quark or a lepton was composite, it would have a form factor. And so you would look at the photon vertex, and there would be some structure to that vertex, and then maybe you could try to measure that. And so actually, we thought about this, and Eichten and Lane and I had a better idea, which is that if electrons, let's say, or quarks are composite, if they're very small, when they hit each other, they can exchange the bosons of the new strong interactions that binds them. And so instead of this, maybe the thing we should look for is a contact type interaction, where some quarks, for example, would come in, and there would be a hard interaction by which they would scatter. And essentially, the size of this interaction would be some measure of the physical size of a composite quark. So then you can start writing down equations for this, and immediately what you find are dimension 6 operators. So in particular, for the electron, we wrote the following thing, 2 pi over lambda squared. Maybe if you really go to the unitarity limit, you would put 4 pi over lambda squared. Eta LL times E left, plus 2 eta RL, E left, E right, plus eta RR, E right, E right. Now, of course, this compositeness stuff is well above the weak scale. So E left and E right are totally distinct species. And so we don't know what the etas are. These eta coefficients might have any relative sign. For example, the left-handed electron might be composite and the right-handed electron could be elementary. And that's perfectly consistent with our knowledge from standard model experiments. So we had to keep these 3 parameters free. But nevertheless, if you think about it, those are the only operators of dimension 6 that contribute to a vertex like that. So there are only 3 parameters. And if you do Baba scattering, all 3 parameters come in. And actually, because Baba scattering involves both photon and Z exchange, you can actually distinguish the 3 operators. So we said, oh, this is really cool. Let's define things so that the largest of the 3 eta parameters is 1, and then we can associate this scale lambda that appears over here with the compositeness scale, that is the inverse size of a composite electron. Now, the thing which is really nice about this is that if you draw the diagrams for Baba scattering, there's photon exchange, Z exchange, and this contact. And you can see that these 4 diagrams are of order alpha, whereas this diagram doesn't have an alpha in it because it comes from strong interactions. And so the relative size of this diagram is 1 over alpha lambda squared, which means it's 100 times more sensitive than looking for the form factor. And so, we were so happy. So very soon, people did experiments with Baba scattering at the accelerators available at the time, and they never found any effect. But they put a limit on the size of the electron, which is about 10 to the minus 19 centimeters, 18 centimeters, which I thought was extremely impressive. Actually, at LEP2, this has gone to 10 to the minus 19 centimeters. Or to put it another way, at a center of mass energy of 200 GeV, you can get a bound on the lambda parameter, which is less than 8 TeV. So you really get to look very hard at the, if you like, the physical size of the electron as measured by a process like this one. I think I have here the Yeah, so here are the exclusion limits for LEP going to various kinds of, E plus E minus going to various kinds of leptons and hadrons. And of course you can write operators like this for all of these E plus E minus processes. And L, L, R, R, V, V, and AA are different choices of the eta parameters. And you can see that all of the limits are at the 8 to 10 TeV scale or above. So this kind of analysis, unfortunately, it doesn't show a disagreement with the standard model, but it really gives you a power which is much greater than you might originally have thought to exclude the compositeness of the basic particles of the standard model. Interestingly, it's hard to do better at hadron colliders. Here there are 3 operators. If you think about quark-quark scattering, there are 17 operators. And so in our paper, we suggested that to analyze this with quarks, you should just include one operator, eta LL, the sum of all quark species, q bar gamma mu q, left-handed squared. And well, that's still where we are in hadron colliders. At the LHC, people put limits on this lambda parameter, which are, I think, about 15 to 20 TeV. But of course, there are 16 other parameters which, in principle, could interfere with this. And it's really very difficult to do better unless you can cleanly distinguish the various flavors and helicities of leptons at the LHC, which is just really incredibly difficult. Okay. Good. Okay, well now probably we should discuss just very briefly the S and T parameters. The S and T parameters actually fit into this context because we can write dimension 6 operators that generate the S and T parameters. So for example, here are some operators which maybe it's slightly non-obvious what the connection is, but let me just begin by writing them down. CT divided by 2V squared, J mu Higgs, plus 4GG prime CWB over MW squared times phi dagger phi times W mu nu. Oh, sorry, I need something better here. Okay. Where J mu phi is phi dagger D double arrow phi, which is equal to phi dagger D mu phi minus D mu of phi dagger phi. So J mu is the U1 Higgs current. This is the SU2 times U1 field strength. That carries an SU2 index, but you can soak it up with this operator. So this is dimension 6, and you see that this is also dimension 6. Now, there are some nice properties of these various objects. Probably this one is the easiest to understand. This one gives you photon Z mixing. And so it actually contributes to the 3Q vacuum polarization that I talked about before. This one, if you plug in the Higgs vacuum expectation value, reduces to minus G over CW. I think there's a factor of 2. Z mu plus dot dot dot. Okay, it also has Higgs couplings in it, but if you set the Higgs boson equal to 0 and you just evaluate it with Z, the thing that survives is the Z in the covariant derivative, and you get an expression like this. So this expression then, so this is a contribution to S, And this expression gives you basically a delta mz squared, which is not balanced by a delta mw squared, so it's a contribution to T. And I don't remember, but I have in my notes the exact relation, namely alpha T is equal to CT, and alpha S, I think, is 32 sine squared theta W times CWB. These are actually not the only way to generate S and T parameters with dimension 6 operators. But at least you can say that these operators, if you induced them by integrating out some higher mass degrees of freedom, would generate S and T. And if you think about that process, it gives you some idea of the magnitude of this CT and CWB operators. Once again, they're of order v squared over m squared. The current bounds on S and T are something like 0.1. And so, unfortunately, if the new physics is at the TeV scale, we're not quite at the level where we're unambiguously sensitive to it in these equations. Okay. It turns out that that U operator, the third one of these combinations, is only generated by dimension 8 operators. And so the effective field theory actually gives you a reason, which is better than just it never seems to be large, to omit U and do fits in terms of the two parameters S and T. The U appears in this systematic approach that I explained at the next order in the systematic perturbation theory. Okay. There's one more application of these methods which is very much in use, and that is the study of E plus E minus to W plus W minus. So here, I told you part of the story on Tuesday, but let me tell you a little more of the story now. So as you remember, on Tuesday, we drew the standard model tree level diagrams that contribute to E plus E minus to W plus W minus. And we noted that each of these diagrams individually has bad high energy behavior. Basically, it's a power of S over mw squared larger than is permitted by unitarity. However, when you add the three diagrams together, there's a miraculous cancellation, and all of those S over mw squared terms go away, and you find a behavior which is not only consistent with unitarity, but also beautifully consistent with experiment. So far so good. Now, people in the 1980s asked the question, maybe we should think of this as a test of SU2 cross U1 gauge symmetry. If SU2 cross U1 gauge symmetry were violated, or to put it another way, if the vertex that appeared in this diagram was not exactly the vertex prescribed by Young and Mills, then the cancellation would not occur, and we would get extra terms, and those extra terms would be enhanced by S over mw squared. Of course, now this kind of an argument makes no sense. I mean, we've done the precision electroweak experiments. They brilliantly agree with the SU2 cross U1 theory. The gauge invariance of the SU2 cross U1 theory is the thing that gives the universality of the Z couplings. That regularity is brilliantly observed. So we're really not going to throw away SU2 cross U1. However, something that you can think about is integrating out theories, some new particles at high mass m, generating the standard model, plus some 1 over m squared corrections, which are parametrized by dimension 6 operators. And for those operators, if those are going to modify these vertices, and actually also even these vertices, and so those can give you corrections to this framework, and those corrections needn't have the gauge cancellations. So the corrections will be of order Ci over m squared, Ci over v squared, but Ci, remember, is a very small number. But then, naturally, they will be enhanced by terms s over mw squared, which appear in each of the individual diagrams. And so this is another way of getting enhanced sensitivity to the dimension 6 coefficients. So let's talk a little about this. I'd like to write down some operators and tell you what their influence is. Here's 4 operators that you can write down. So first of all, g squared CWW over MW squared times phi dagger phi times W mu nu W mu nu. Secondly, this operator, 4GG prime over MW squared, phi dagger TA phi, W mu nu B mu nu. Thirdly, G prime squared over MW squared, CBB, phi dagger phi, B mu nu B mu nu. And finally, G squared C3W over MW squared times epsilon ABC times WWW mu nu lambda lambda mu ABC. And these are all parity conserving, CP conserving interactions that they do 2 things. The first thing, which is kind of obvious, is that they will modify the gamma WW and ZWW vertices. For example, this is a completely new structure that one can find in these vertices. Also, remember that this term and this term, the W has terms which are quadratic in W fields. And so these 2 terms can directly influence these interactions. The second thing that happens is that if you set the Higgs field equal to its vacuum expectation value, then these become new just terms that are quadratic, the first line at least, terms that are quadratic in the W and Z fields, and actually also the photon field. So we get some wave function renormalization, or as I like to say better, field strength rescaling terms. 1 minus ZW is 1, please excuse me, plus 8 CWW. This way. ZZ minus 1 is equal to 1 plus 8 cosine squared theta W CWW. They're terms that involve all 3. And the actual coefficients you can read when you see the slides. There's a correction to the photon field strength renormalization, which is also a renormalization of alpha. And also, because this term and this term are not diagonalized with the sine squared theta W that appeared at the tree level, there's a delta Z, a gamma Z mixing term, which is also proportional to these things. 8CW squared plus dot dot dot, that you have to add as a new vertex in perturbation theory. Yes?
These are quadratic. Can they also provide mass corrections?
No, because they're field strengths. They're all proportional to Q squared. Okay, so this operator I showed you provides a mass correction.
Yes.
But among the dimension 6 operators, that's actually the only operator that gives you a mass correction. Okay, so actually at the tree level, dimension 6, you don't have to rediagonalize between the Z and photon fields. The masses remain in the original basis. But you need to include this insertion in perturbation theory to take into account the fact that the kinetic energy terms have a slightly different basis. Okay? Good. So all those terms mean that every time a Z or a photon is emitted somewhere in a diagram, I have to rescale the vertex by the square root of this effect. So you can do that systematically, and what you end up with is the following structure. So now, if you go into the literature, when people were still talking about violation of gauge invariance, they said we can parameterize corrections to the standard model 3 gauge boson vertex just on the basis of QED gauge invariance and Lorentz invariance. And they wrote the following expression: I times GV times W mu nu sorry, it's a 3 gauge boson interaction. So I'm thinking about V going to WW, where V is equal to gamma and Z. So this is V mu W nu, something like that. Then there's another structure that can appear, which is V mu nu W mu W nu. V mu nu is the magnetic field associated with V. So this is like a magnetic moment correction. And then there's also a term which is called lambda A, lambda V over mw squared. V mu nu W nu lambda W lambda mu. Okay. And so this formalism introduces 3 parameters for the photon, namely GA, kappa A, and lambda A, and 3 parameters for the Z, namely GZ, kappa Z, and lambda Z. Now GA is the electric charge of the W boson. And so it had better be true that GA is equal to E in all of this perturbation theory. And indeed, that turns out to be true. Basically, there's a cancellation between the A rescaling that comes from this and the terms that correct the 3 gauge boson vertex. Those exactly cancel, and so you get no correction. All of the other parameters are corrected, but in a pattern which is kind of interesting. In particular, lambda A is equal to lambda Z, and it's proportional to the C3W parameter, which is the one that introduces the new structure that appears here. The GZ is shifted by cosine theta W. I think the delta Z A minus delta ZZ. I'm sorry, I should have shown you the slides rather than, excuse me, sine squared over cosine squared, something like that. And the kappa A and kappa Z are also connected to each other. This is 1 plus 8 CWB and this one is 1 minus SW squared over CW squared times 8 CWB. And yeah, we're good now. Okay, so interestingly, there are, from Lorentz invariance and QED gauge invariance, 5 possible deviations. But actually, there are only 3 independent ones. Because there's this, these two guys are related, and these guys are related because they come from the same dimension 6 operator that I wrote up here. And then the violation of these relations would come at dimension 8. So basically, SU2 cross U1 predicts some additional relations among these parameters, which I've written on the blackboard. And one can either use that to constrain a fit to the data, or let everything be free, and then you're actually doing a test of SU2 cross U1. Of course, you would expect that test to succeed, but nevertheless, it's interesting that there is such a test. So we've learned some interesting things. These are all basically formalisms that have been compared to experiment. And what they tell you is that the effective field theory approach allows you to parameterize deviations from the standard model in a way that both organizes those deviations, relates them to a specific set of operators, tells you what the SU2 cross U1 predictions are for deviations. So it basically tells you that some deviations are expected to be large and some are expected to be small in an SU2 cross U1 invariant theory. And actually, it can even give you precise relations among different deviations that can be tested, or, as I say, used to improve fits. Now, these expressions are being tested at the LHC, and some of you might even be working on that. And so I'd like to inject a note of caution to those people who want to think about these constraints from vector boson interactions, and actually also similar things. This also comes up in the study of Higgs interactions at the LHC. What I've emphasized already is that the corrections that come from these interactions, when you actually compute the cross-section, they get enhanced by a factor of S over mw squared, or maybe if we're dealing with LHC processes, S hat over mw squared, the parton-parton center of mass energy. Now, parton-parton center of mass energies at the LHC can be extremely large. They can run up to, well, close to the full center of mass energy of the problem. So they can be 4 or 5 TeV easily, which means that you can get out W pairs which have a center of mass energy of 4 or 5 TeV. And then you get a huge enhancement. But the problem is that, like the case before, this expression will nominally violate unitarity. And so at some point, this formalism has to go bad. And actually, we already see how it's going to go bad, because all of the analyses that I've described would be the standard model plus corrections of this order, Ci over V squared, S hat over mw squared. Now, if you put this in the amplitude and square it, there will also be terms of order Ci over V squared, S hat over mw squared, squared. But also remember, there are those dimension 8 operators that we forgot about, but now let's put them back, di, which naturally have S hat squared over mw squared just from their own dimensional analysis. So when these terms are important, also probably these terms are important, and then you really lose control over the whole analysis. So different people have different attitudes toward this. I guess my attitude, again, is very curmudgeonly. I would say when these terms are important relative to these ones, S hat is too high, And you need to restrict the region that you're going to look at, so you only consider W pairs which have a smaller center of mass energy. Other people, Riva, Falkowski, there are many people who have this idea, say, in WW scattering, this term turns out to be exceptionally suppressed due to some helicity effects. This is actually a very nice observation. But then they say, well, then it's okay to go into the region where these terms are important. And let me just show you a couple slides here. Yeah, so this is from a paper by Falkowski and collaborators, where they reanalyze some data that was shown by the CMS collaboration for WW scattering in terms of the parameters GZ and kappa gamma, or kappa A, I've called it over there. So this is the region, the blue are the constraints that come from LEP2, and LEP2, the center of mass energy only went up to 200 GeV, so it's pretty clear that stopping at the linear order in C is a good approximation. At LHC, you can go as high as you want, and the CMS people actually went quite high in this analysis. And so what you see here, the dotted curves, are the result of analysis that stops at linear order, and the solid red are the constraints that come if you include the quadratic terms, but of course drop, because they're not included, the DI terms that can certainly confuse the analysis. So then you can ask the question, which is right, the solid red or the dotted red? And the answer is probably that neither of them are right. So this is something that if you want to publish a paper on this, you really need to think about deeply. This group also published some interesting figures where they just constrain MWW and reanalyze the data with those constraints. And basically, this is the whole CMS data set. The outer curve is restricting MWW to 600 GeV, which is now everything is probably okay. And the true limits from LHC lie somewhere in between, as you see. So, well, as I say, when you try to analyze LHC data with terms that are enhanced by S hat over MW squared, you're playing a game with the devil, and you have to really watch your cards very carefully. And those of you who want to work on this, I encourage you to think about that. Okay, now finally, I'd like to discuss something that really hasn't come into play yet, but it will, which is the discussion of the deviations of the Higgs observables in this framework. So there are actually two distinct effects which Nathaniel actually referred to yesterday. One of them would come from a dimension 6 operator like this. So let's just write yt over v squared, phi dagger phi. Let's think about the process Higgs to tau plus tau minus for clarity. The L dot phi tau plus Hermitian conjugate. Now this is an interesting operator. First of all, it gives a tau mass, which is equal to the following thing. First, we had the Yukawa coupling. So the tau mass formula that we wrote yesterday was something like this. The tau mass is equal to the Yukawa coupling times v over the square root of 2. This will add to that. I set phi dagger phi equal to its vacuum expectation value. And I generate and I need a coefficient here, c tau phi. 1 plus 1/2 c tau phi. Now I can also ask, what is the coupling of Higgs to tau tau? And that, as I told you yesterday, is given in the limit of light Higgs by differentiating this expression with respect to the Higgs field. Except now the Higgs field appears 3 times. And so this is y tau, and then it's got a 1 plus 3/2 c tau phi. So there's a mismatch now generated by the dimension 6 operator, which will mean that the standard model prediction, which is based on this, will not be valid when you measure the Higgs coupling by an amount proportional to c tau phi. Now actually there's another operator that also contributes, which is this one. So that's also a dimension 6 operator. And what that can do, if you work it out in terms of Higgs fields, is that it's d mu of the Higgs field squared times CH, I think minus CH over 2. And no. And so this will give you a field strength renormalization for the Higgs, which is 1 minus CH. And that will be a renormalization which is applied to all Higgs couplings. And so at the end of the day, what you find is that the partial width of Higgs to tau tau divided by the standard model value is changed by both of these effects. There's a 1 minus CH, 1 minus a half CH plus c tau phi. And this one is basically let's just see if I got those coefficients right. No, exactly wrong. Times 2. Okay. So this is universal over all Higgs couplings. This is this mysterious universal rescaling that Nathaniel referred to in his lecture yesterday, actually discovered by Nathaniel, so that's a good reason why he talked about it. And this is a shift which is particular to the specific species that you're looking at. And actually, hopefully both of these have to be determined, and what we'd really like is that they are determined independently when you evaluate the corpus of experimental data. Okay. Now, every time I discuss a new process, I'm getting more parameters. So there are two things that are happening here which have to be balanced against one another. On the one hand, this parameter CWB has already appeared in two quite different places in the analysis. So you would think that if I look at the whole corpus of data and do a joint analysis with both E plus E minus to W plus W minus and Higgs data, then maybe I can fit out some of these parameters that appear multiply, and then I could do better. On the other hand, the whole number of parameters is obviously multiplying. And so now we really have to take this question seriously. How many parameters are there really? And do we have enough observables to get a handle on all of the parameters? So I'm going to discuss that in just a moment. First of all, there's one comment I should make about this analysis, which is actually somewhat important. You remember that yesterday we talked about the natural flavor conservation of the standard model. That is, when you write the Higgs vertex of the standard model, let's say again for taus, y lepton ij, Li dot phi tau or E right j, we could write this in the standard model, and y could be an arbitrary complex 3x3 matrix. But I could diagonalize that matrix. The various unitary matrices that do the diagonalization can be transformed away. Actually, from the minimal standard model, they actually disappear if there are no neutrino masses. And so there are no lepton flavor violating effects in the standard model, again with zero neutrino mass. Now what I suggested is that when you consider these dimension 6 corrections, you add Li dot phi E right j phi dagger phi. So this is a new operator. And a priori, there's no reason why this matrix should be related to this matrix. In fact, there's no reason why this matrix should commute with this matrix and be diagonalizable in the same basis. So the beautiful thing that we had before, that the Higgs couplings never violated flavor in the standard model, is lost when you go to this effective field theory. And that's just a reflection of the fact that it is lost in a generic beyond the standard model theory. Now, fortunately, this coupling here is small. It's proportional to v squared over m squared, and m could be large. So maybe this flavor violation is there, but it's just at such a small rate that we won't be able to see it. But nevertheless, it's something that you have to worry about. So there are two alternatives. Either you build your BSM theory in such a way that it has a flavor conservation symmetry that will guarantee that there's, if not a relation between these matrices, at least there's a conservation law which is shared by them. Or you would expect that some small rate decays like Higgs to tau mu. And I think it's fantastically important to push down the bounds on Higgs to tau mu. Some of you might remember that briefly there was a CMS sighting of Higgs to tau mu that went away. It was just a statistical fluctuation. But one shouldn't be discouraged. This could really be there. And it actually could be the first hint of a flavor-dependent new physics beyond the standard model. Okay. So, okay, now we're doing great. Oh, sorry. One more thing I wanted to say before I got into the general discussion. For Higgs to tau tau, there are only these two operators. But when you consider, for example, Higgs to WW, there are more operators. For example, let's consider the following. First of all, there's this operator, which is always there for every kind of Higgs coupling and gives an overall shift of the Higgs couplings. But for Higgs to WW, there's also this interaction that we wrote down before, CWW over G squared MW squared times phi dagger phi times W mu nu W mu nu. Well, here I can get a Higgs field. So this is actually an explicit correction to the Higgs to WW coupling. But oddly, its structure is different from the structure of what you get from the CH. So in fact, the coupling of Higgs to WW has now two different Lorentz structures, which are in principle distinguishable. I like to call them A to Z and Z to Z. So this is the one that appears in the standard model. And it's also the one which is corrected by the CH effect over there. But then separately, there's something which I like to call Z to Z, 1 over V, W mu nu, W mu nu. So there are two different structures here, and they arise from two different sources. This one from basically the Higgs field strength renormalization. This one from some new operator coupling that has to do with heavy particles that couple to the W field strength. And part of the problem of extracting the magnitude of Higgs couplings will be to measure A to Z and Z to Z separately and to try and disentangle them. That's something that goes beyond just simply measuring the rate for Higgs to W plus W minus. Okay. So now I've eaten up a lot of my time. There's 15 minutes left. But now we really have to open the gates to a lot of complication. So if it goes too fast, please excuse me. Let's try. So now we come to the following question. We've introduced a very large number of operators. Some of those operators do appear in different processes. For example, we already saw CWB in 2 processes. Here we see CWW, which also appears in the W pair production. But at the same time, every time we introduce a new process, we seem to keep introducing new operators. So where does it end? Well, eventually it has to end because there are only a finite number of dimension 6 SU2 cross U1 invariant operators. So how many are there? Well, you can try to answer this question by making a list of them, and you will find many, many, many. But probably that list is too long because, as I told you already, you're allowed to cross out operators which are 0 by the equations of motion, and that makes the list shorter again, although let's just say it's not as powerful as your ability to dream up new operators. So this question actually was not analyzed for a long time, but finally in 2010 it was analyzed by, and please excuse me for my Polish, Grzyszewski, Iskrinsky, Misiak, and Rosiak. And their answer is called the Warsaw list for the obvious reason that nobody can spell Polish names. And it consists of 59 dimension 6 SU2 cross U1 invariant operators made from the known field content, which are not reducible by using the equations of motion. Oh, and maybe I've also assumed baryon and lepton number conservation, so there are more if you relax that assumption. Okay. Oh, and this is also, maybe I should say, for one fermion generation. You can replicate these operators if you have multiple generations. So this is genuinely scary. I must say that this number had turned me off this subject for many, many years. Because as I've explained to you, I've done these analyses with like 3 operators and 2 operators and 3 operators, and it seems like everything is perfectly under control. But when you ask me to do an analysis with 59 operators, it just seems like garbage in, garbage out, and what can you do about it? Now, unfortunately, at the LHC, it's almost impossible to overcome this problem because you don't have polarization observables. You have many quark species. Each quark species, as it were, generates its own set of operators. And so the list of operators that enters any given process is extremely large. As I'm about to discuss with you, if you have QQ bar to W pairs, the dimension 6 operators also affect this vertex. And actually, they also affect the neutrino diagram. And properly, all of these effects should be taken into account if you do a joint analysis of the W data, for example, with precision electroweak and with Higgs data. So the problem really just becomes extremely difficult. However, I must say, prodded and encouraged by my E plus E minus experimental colleagues, we found out that this problem actually is solvable for E plus E minus colliders. So the advantages are, first of all, you get to deal with only the electron. Secondly, you have polarization observables, which can be very important. I'll give you one example as we proceed. And so a bunch of us wrote a paper where we consider a set of 17 observables. So we considered E plus E minus precision electroweak. Actually, this is leptonic precision electroweak. So one of our inputs, for example, is the Z width to L plus L minus that doesn't have any quarks in it. E plus E minus to W plus W minus. and a very interesting process, E plus E minus to ZH, which I'm going to discuss in detail. We consider 17 operator coefficients, plus, of course, there are 4 standard model parameters that you have to vary. And then we actually also threw in 2 parameters for exotic Higgs decays. So the claim is you don't actually know the normalization of Higgs due to the fact that it might decay to either invisible states or some exotic states that you haven't bothered to look for. So that's a lot of independent variables. But then it turns out you can go through, and at least in this context, find observables that determine each of these operators more or less separately, or small sets of them more or less separately. So you can actually solve the problem. And let me just say a few things about that. Maybe yes?
Do you have a reference to the paper?
It's in the notes.
Okay.
So maybe I should show you this list of operators. Okay, here we go. So a lot of these you've actually seen already. So at the top, you see the operator for the Higgs field strength renormalization, the operator that gives the T parameter. This operator shifts the triple Higgs coupling. And actually, it's actually not included in this analysis because it actually doesn't come into any of the processes that I'm discussing. In the next 2 lines, you see the operators that I've discussed for E plus E minus to W plus W minus. In the next 2 lines, you see some operators which are Higgs currents. You saw that guy up there, times leptonic currents. So for the electron, there are 3 of those. And they come into the leptonic side of the precision electroweak experiment. Actually, when we did the analysis, we assumed these parameters were the same for E mu and tau. But I think it's pretty easy to relax that assumption. There is a current operator that contributes to G Fermi, which is not on this list, which can be separately constrained by E plus E minus data. And then there are these helicity flip operators that give you the direct corrections to the Higgs currents. And actually there are, in this context, you can sum up all the corrections to the Higgs glue-glue vertex in a single dimension 6 operator. Typically, that's written as a sum of 3 different coefficients. And then finally, there are 2 more operators not written here, which have to do with the hadronic side of precision electroweak. And now, what I should do, except I'm really running out of time, is to try and explain to you how all of these factors can be. So there are 2 things that I have to say. First of all, this is it, because actually, according to our friends in Warsaw, if you consider operators that only act on Higgs, Z, W, and gamma, you can remove all other possible operators that you could write down by using the equations of motion. So fortunately, until we introduce fermions, this set of operators gets very small, because of the powerful use of the equations of motion, basically to push other operators onto the fermion side. And then if the only fermion that appears is the electron, then you have these operators plus those electron contact terms that I showed you at the beginning of the lecture, which actually are not relevant here. Then you need some operators for the Higgs decays. There are some other Higgs operators which are of the magnetic moment form that do not contribute to the rates of Higgs decay. And then as I say, 1 operator for the gluon, and then 2 more operators for the hadronic side of precision electroweak. Now, probably, I think I've explained most of the.
There are also these CPO couplings to the
Oh, yes. Did I put that on the next slide here? No. So we're only going to consider in this analysis CP even observables. But there are other observables which are CP odd observables. So there are 4 additional couplings I should have written down here which are CP odd. However, those are separately controllable by different experiments. For example, if you look at E plus E minus to Z Higgs with polarized beams, the forward-backward asymmetry is controlled by a CP odd observable. And if you just bound that forward-backward asymmetry, you limit the CP odd observable. And then it only comes into this analysis at order C squared because we look at CP even observables. So you have to test for this. But given that the CP odd observables are 0, they don't contribute to the analysis that I'm going to describe. Let's see. Must be something else I have to tell you. No, we're good. So probably, can I have a few more minutes? Okay, we're getting there. I want to tell you a couple things about E plus E minus to ZH, this very interesting process. And then I'll just quickly run through a slideshow, and then we'll be done. E plus E minus to ZH is a fantastically interesting reaction. And I think people worked on this. Nathaniel actually wrote a paper about this in effective field theory. But I think it's only with our study that people have realized how really fascinating it is. It's been known for a long time that this is a great way to study the Higgs boson because it recoils against a Z, and we know the masses of everything. So, for example, if you're at 250 GeV in the center of mass, the Z is at 110 GeV measured in the lab frame. If you see a Z at 110 GeV, up to small corrections from radiative E plus E minus to ZZ events, what it's recoiling against is a Higgs. So you just count them, the BB bars, the glues, the CC bars, the taus, the invisible, because the tagging Z makes it visible, or even partially invisible decays. I think on the next slide here I have some figures from a CLIC Higgs analysis group study. So here's some simulated data, and then there are machine learning parameters for the BB bar and CC bar likelihood. And then you see how that separates the data into the components from glue, BB bar, and CC bar, and various kinds of backgrounds. So unlike the case of the LHC, if the Z decays hadronically, you can really diagnose what kind of hadrons it decays to with all the possibilities covered. The second thing, which is very interesting for our purpose here, is that this process depends on polarization in an interesting way. So actually in effective field theory there are 3 diagrams, because this vertex is generated by the ZA mixing term that I told you about. And there's also actually a contact term, which is generated by, if you look here, oh, sorry, should have done it here. If you look here, the operators that involve precision electroweak interactions also have Higgs fields in them. So you can get new Higgs vertices from these, which look like contact interactions of the kind that I drew here. These turn out to be not so important because precision electroweak on leptons is a strong constraint. These two have an interesting interplay because what they do is that there is the term that gives you the shape of the angular distribution has constructive interference between these diagrams if the electrons are left-handed. And when the electrons are right-handed, the sign of the E plus E minus Z coupling changes, and you get destructive interference. And so the polarization asymmetry of the cross-section then gives you a handle on the parameter zeta independently of the parameter eta. And so it allows you to pick the components apart. So now we're great. Now you throw this into a big pot. You have 22 parameters. You have lots of observables, including these angular distributions and polarization asymmetries. So actually every parameter has something that is constraining it. And you can actually do a controlled multidimensional fit for the whole set of parameters. And then, let's say you may have simulation data, which is the standard model. Then there's some covariance matrix for these parameters. And you can then give a prediction of how well each parameter can be measured or constrained. One of the interesting ways of displaying this fit is to interpret it in terms of bounds on the Higgs couplings. Because once you have the covariance matrix, you can then quote an error with which you measure each individual Higgs coupling. The Higgs couplings, because you've in the process determined the parameter CH, or eta, the Higgs couplings come absolutely normalized. And so both the relative and the absolute size of the Higgs couplings is constrained by the fit. And I think the next slide is probably a table of the results. And we just ran the program for the program of all the proposed next generation E plus E minus Higgs factories. So these are individual Higgs couplings that you see on the top and the projected error in percent. So for ILC, for example, 1% on the BB bar coupling, 0.7% for the W and Z couplings, et cetera, et cetera. The width of the Z is actually determined to 2.5%. So that's required to understand the normalizations of all of these couplings. And if you plug in the event samples for other proposed colliders, for example, CEPC 5 inverse Atabarns is the event sample that they claim, but however, without beam polarization, you come to very similar results. So basically, if anyone would like to give me any of these machines, I'll take it. And for ILC, there's the interesting thing that you could do an upgrade to 500 GeV that basically halves the errors. So I should be over here. So this is the figure we put out for ICFA to demonstrate the power of this machine. The red bars are the projections for the full high luminosity LHC from Atlas. This, I guess, will be redone this year. The light green bars are the ILC at 250 GeV, the first stage. And if you did the second stage at 500 GeV, you get the dark green bars. The 1% level of couplings is here. So you can see that this machine, in principle at least, can meet the goal of measuring the most important Higgs couplings to an accuracy below the 1% level, which really would be required for a tight comparison between Higgs data and beyond the standard model theories. Now, in our paper, we played a little game, which I'll just show it to you, see what you think. We wrote to many of our friends, and we asked for, beyond the standard model models, that, first of all, the particles are too heavy to be discovered at LHC. Secondly, the effects on the Higgs couplings are somewhat large, so that in a precision Higgs analysis, one could expect to discover the anomalies. And we asked for we wrote to many people and asked for models of many different kinds. So there's what's called PMSSM. It's a supersymmetry model with squarks at 3.4 TeV. It turns out to be very easy in supersymmetry to have B squarks at 4 or 5 TeV, making large, that is to say 5% or more, corrections to the BB bar Higgs coupling. There are various kinds of type 2 Higgs doublet models on this list. Remember, I told you there are 4 kinds, so this is type 2, X and Y. There's a, quote, composite Higgs model of the kind that Christophe Grosjean has put forward. There are 2 different little Higgs models which differ in the way the little Higgs is giving mass to the light generations. Higgs radion mixing, I won't explain what that means. And a model with a Higgs siglet that generates a first-order phase transition that you would like for electroweak baryogenesis. And as it says here, your additional suggestions would be welcome. Then these all predict some different pattern of deviations from the Higgs couplings. And those are shown here for 4 of those models. So we're going to measure each of these individually, BB bar, CC bar, GLU, WW, etc. And every kind of model predicts different effects. For example, Susie likes relatively large effects in the B and tau couplings. Two Higgs doublet models also like that, but in some different pattern. Composite Higgs especially likes deviations in the W and Z couplings, and sometimes also in glue-glue. And the Higgs radion mixing likes to move the gluon coupling without much moving any of the others. And you see at the level of the error bars I'm quoting, those patterns are distinguishable. So you actually learn something, not only that there is physics beyond the standard model, but you learn something about what kind of physics is there. So my colleague, my colleague Jenny List made a scorecard for these models. So the first column is the discovery of the model, that is the deviation from the standard model. And then here is the ability to tell one model from another. Red is below 3 sigma, orange is 3 to 5 sigma, light green is 5 to 8 sigma, and dark green is above 8 sigma. And then if you would do the energy upgrade of the ILC to 500 GeV, it looks like this. And now you're really in business. Now you have definite clues about where to go in building models beyond the standard model. So I just think this is incredibly cool. I hope you agree.
So Michael, in these models, your operators are generated at T level, basically?
Sometimes by loops, in supersymmetry by loops.
Because you see coefficients between V square over mu physics.
Yeah.
1%.
Right, but that's the order of magnitude. So here we asked people, what's the prediction in your model? Okay? There's a table of these things in our paper, so you can go check it. So in this lecture, I've tried to argue to you that this standard model effective field theory is a very powerful method for discussing the search for deviations from the standard model when you do precision experiments. It allows us to evaluate effects that we've seen so far, evaluate the limits that we've achieved. It also allows us, it also gives us a nice tool to estimate the capabilities of future accelerators. And as I hope you've seen, these really turn out to be very powerful in exploring for physics beyond the standard model, beyond the reach of LHC. So I hope also I've communicated to you a little of my enthusiasm for the lepton collider as opposed to hadron collider route to beyond the standard model physics. And well, you can take it from there. Thank you very much. Okay, so sorry for running over time, but maybe I can take a question or two. Yes?
Yeah, so I didn't get like in the last talk, so for the future collider, so what did you show there? You cannot show any deviation from the model if you don't have the collider.
Oh, what I'm showing is basically the covariance matrix that comes out of the fit. So if the real value is 0, what is the standard deviation of the measurement? And so that's something you can compute, and then you can try and do something with it. So in particular, we use that covariance matrix to evaluate the ability to distinguish different models from the standard model. Okay. Anyone else? Yes?
I guess I have a follow-up question on this idea of using the equations of motion and such things.
Yeah.
There's only 17 operators that contribute at the lepton collider, but wouldn't other operators have an effect on like the field strength normalization of the Higgs?
No, because that's an operator that reduces specifically to d mu h, d mu h. So there are several such operators, but typically what it is that they're related by something on the right-hand side which has quarks on it. So why don't I get rid of one of these two operators and put the quarks, but the quarks have no effect on the processes I'm interested in. And so this operator completely encapsulates the change in the field strength that comes from dimension 6 operators. And so that's the strategy that's used to reduce the operator basis. And I think it's correct. Okay. Good. Well, thank you very much for your attention. I've had fun. I hope you have as well.